Zoom recording. Chapter 6. Chapter 6 starts off, and as you can see, I've kind of built this out. I've actually built out 2 full pages. Chapter 6, I doubt we're going to get through it today, and if we do, then it's, oh, that's right, we're going to, just review. All right, let me think about that. I wasn't really prepared for review. Let's start with chapter 6. I want to get going on that. So this chapter starts off on a subject I've already mentioned. I really don't like logarithm, and I realized when I was preparing for this, one of the reasons I get confused by logarithm is that what they show in the book is only one narrow type of logarithm. And that's base 10. And that's fine. That's all we really need to know, and we really don't need to know it that well either. We pretty much just all we really ultimately need to know with this is that logarithm, every step up, every numerical step up in a logarithm is huge. When we talk about the Richter scale for earthquakes, the difference between 5.0 and a 6.0 isn't 1 point or even 10 points. It's 100 or 1 times. Let's say between 5 and 6, you might think, well, it's just one, one more, 1 times as much or 2 times as much. No, it's like 100. So every number you go up is 100 times the previous number. So between 1 and 2 is 100 times. And then whatever that product is between 2 and 3, 100 times that. And so these numbers become very large very fast. So with logarithm, I mean, I understand why they have it, but exponents to me are easy enough. Whoops, an exponent 10. And when it comes to tens, it's nice. 10 to the third is 1,000. 10 times 10 times 10 is 1,000. And 10 to the 6 is 1,000,000. And that actually works out really well. It only works out with tens, but that 10 times 10 times 10 times 10 times 10 times 10 times 10 is 1,000,000. And so it's nice though. You just write zeros for 10 to the 6. You just simply write 6 zeros, and that works out really nice. And that's base 10. But if you have a base of 2, things aren't as quickly and easy to you can't just add zeros. So 2 to the third is 2 times 2 times 2 is 8. 2 times 2 is 4 times 2 is 8, yes. 4 to the 6, well, this one I had to pull a calculator out. 4 times 4 times 4 times 4 times 4 times 4, 6 is 4,096, which is a huge difference between 4,096 and 1,000,000, but that's because our base is 4. So that's just that's not logarithm. This is just exponents. Exponents, they make sense to me. There's another you could also do. It's also counted as exponents to do 1 times 10 to the 6 or 3.51 times 10 to the 6. You're still just counting decimal points. So those are also exponents as well. And actually, what would this one be? I guess this would be 3,351 million. So whoops, hit the wrong spot. 0, sorry, 0, 0, 0. 1, 2, 3, 4, 5, 6. Yeah, I believe. I might be 1 point off. I don't care because I don't care about these numbers anyway. We just need to basically understand what's going on. So logarithm, it's there to, it's just simply to handle really big numbers. So you're not writing out 0, 0, 0, 0, 0, 0, 0, zeros all the time. Most log scales, the hurricane, that's what, Fukushima, earthquake is Richter, they use base 10. And so that's an easy base to get to, or it's an easy one to deal with because basically every step of the way is like 100 times the strength, 100 times the energy. So up here, let's use yellow. This 10 to the second, that's an exponent. 10 to the second, 10 times 10 is 100. That's an exponent. In log, it gets a little, I drew arrows to kind of bring everything around. The log 10, so that's your base 10, and I am not going to have you guys work any of this out, so take notes, just pay attention, whatever you want to do. Log base 10 to get to the product. So getting to this number 100 is 2. 2 being the multiplier. Multiplier up here. The multiplier is the answer getting to this number, the product over here. That's very hard to follow. Don't worry if you're not following it, or if you do follow it better than I do, then you could take over the class. I would be more than happy. Ultimately, why do we care? Because sound is measured in decibels. Decibels are logarithmic. So logarithm. Decibels are logarithmic. The other thing about decibels is they are a relative number. People don't really, and I never really think about it. So a decibel is not an absolute number. We think of, you see the old time stereo systems, they'd have a dB for decibels. And it just seemed like, well, 60 decibels, that's where you want to be, man, because it's really loud. But when I say it's relative, it's always compared to something else. So usually when we're talking about, let's say, a stereo system, or they say a jetliner has 120 decibels if you're right next to the engine, or a whisper is you know what, I think there's, I thought there were some examples of decibels, but in any case, when we talk about a rock concert or a jetliner being 100 decibels or 120 decibels, and there's a certain amount of decibels that are permanently, instantly damaging to, what they're basically saying is that as compared to a butterfly. So, slightly off my screen here. A rock concert is 100 decibels compared to the sound of a butterfly. And so we think of decibels as being an absolute value because everything's compared to the sound of a butterfly, but it doesn't necessarily mean that. If we increase our noise from my current speaking voice, if I increase it 1 decibel, it's not 1 decibel it's 1 decibel from my current voice to a louder voice is a increase in decibels. That's it's just simply a fact that we need to know. Honestly, not going to help us. It's really not. Other than getting this question right on your test or on your SBI, understanding that decibels are relative is relatively useless, and understanding how decibels are logarithmic are somewhat useful, I guess, understanding that when we do change our overall power. Sorry, cats are scratching on things and they're gonna drive me crazy. And so anyway, going forward, here's a little piece of common sense you must know. And I am joking. It is not common sense at all. But these are definitely winners here. You need to know an increase of 3 decibels doubles your intensity. And so and if you work it out with a calculator, it works. An increase of 10 decibels is a 10-fold increase in intensity. In other words, 10 times as much increase in intensity. So 3 is a double, 10 is a 10-fold, which also means a -3 is equal to half intensity. And a -10 decibels is equal to 1/10, because it was a 10-fold increase. A negative is a 1/10 intensity. So these, basically these 4. 1, 2, 3, 4. Definitely want to memorize that. The other thing about, actually I have this written somewhere else. I don't have to say this right now. So, and then I have a little, basically, this is what you need to know. Decibels are logarithmic. Every increase in decibels in the Richter scale is 10 times greater. You know what? Okay, let me double check that fact. Like we just said, 3 decibels increase is a doubling. 3 decibel decrease is a halving. 10 decibel increase is 10 times. A negative reduction in decibels is 1/10. A reduction of 10 decibels is 1/10 the original. So it's always, in other words, 1/10 of the original intensity. We deal with, by the way, guys, more often than not, we're going to deal with the negative intensities. Because when we're talking about this, really the only reason we're going to talk about decibels at all is not so much the power output, but the attenuation. Attenuation is always negative. And so in fact, it's redundant to, if you say 3 decibels of attenuation, the negative is implied. You don't have to say negative, and it would be redundant if you did. If you were to log, a graph logarithm, they tend to look like this. They're up, 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 and they fire straight up like the inconvenient truth. All right. So the parts that we will come around to again with the, like I said, I mean, the important parts, the 3 and the 10, 3 decibels of attenuation and 10 decibels of attenuation. Those will probably come back. There are other, obviously, all sorts of numbers of attenuation, but those two are kind of the easy ones to remember, and so that's what they ask us. Okay, hey Kitty. So attenuation. When things are farther away, they don't sound as loud. That's all attenuation. Well, there's more to it. But obviously, if I walk to the other side of my house and continue to speak to you, you're not going to hear me as well. The sound has attenuated over distance. So the more distance a sound beam travels, the more attenuation we're going to have. Attenuation is greater or faster, it kind of depends how you want to use the English language, with high frequencies. Attenuation is greater with high frequencies. So that's why we use the, I'm going to use my phone as a linear. That's why we use the linear transducer on the neck. We're not going very deep. It's a high frequency transducer. You cannot use the linear on the abdomen. It'll only go, an inch and a half, maybe 2 inches into the body before it is attenuated out. Lower frequencies, like Barry White, low frequencies attenuate less, or it's not as fast, it's slower attenuation. You can use the curve transducer on the neck. Doesn't look too good though. But you could also use it on the abdomen because it goes deeper before that sound is attenuated. It is a lower frequency transducer. Like I said before, attenuation is always a reduction of sound. So when talking about it, you don't need a negative sign. If you say negative 10 decibels of attenuation, that is redundant. You do not need that sign at all. You just simply say 10 decibels of attenuation is negative. Now, I saw this visual analogy of, and I think it's pretty good as to what is happening with attenuation and why the higher frequencies attenuate faster. So I'm going to draw two frequencies going through tissue. And so basically this is tissue layer. Well, these are both tissue layers. But on the first one, I'm going to travel through, just give myself a little, all right. High frequency. I'll do a high frequency on this first one. Oh, I forgot what mode I was in. Let's do this. That's better. And on this next one, I'll do a low frequency. Now, I'm not 100% sure how accurate the analogy is, or how accurate, I don't know if it's even analogies, or how this description is. But at a higher frequency, we're going the same distance here, the sound, this is my boy. Hi, everybody.
I was about to tell you, just pet him a little bit so he can get a little attention.
Over me now. Okay, high frequency going through this tissue layer. As it goes through, I don't know, 2 inches of tissue, it interacts with the tissue every time it goes through a frequent or a cycle. It's interacting with the tissue. A lot of interactions compared to the low frequency transducer, which interacts far less. Like I said, I'm not 100% sure how this description or analogy is to real life, but I do like it.
Kurt, I can't understand what you're saying.
Oh no, am I a robot?
Oh, it got better.
Okay, cool. Yeah, so I was just saying, I'm not 100% sure how well this analogy or this description jives with the real world. But if we think about it this way, all these interactions every interaction takes, I know, every interaction steals energy, takes energy from the system. So these high frequencies with these many waves, they simply interact more, therefore they lose energy faster. So in any case, high frequency thyroid, low frequency liver. You're going to use a low frequency for liver. Okay, let me just look at the book, make sure decibels, attenuation. So frequency and attenuation are directly related. Well, what does that mean? How would you say it? Attenuation is greater in higher frequency. Okay, yeah, if you put it, the attenuation is higher with higher frequencies. So in that regards, they are directly related. Attenuation is lower with lower frequencies. And distance, of course, is directly related. The more deep you go, okay. So what causes attenuation other than just simply this interaction? By the way, this interaction, what I described up here, there's another word for it, really, I guess we can call it. Oh, there's mountain lions out there, you can't go. Heat is really what we're talking about. Heat's not the only thing that causes attenuation, though. Reflection. Now, reflection is kind of important. It's part of what we're seeing is reflected signals, right? So we send a sound beam into tissue. It runs into a larger boundary. When we say large boundary, I mean, if you're talking about a really large, well, no, you don't talk about the anatomy yet. The wall of the carotid artery, so you have your common carotid over here. That is a wall, and that is a large boundary. So sound is reflected, and you'll notice when you look at the carotid artery, it's very bright. On our screen, it's echogenic. The reason why it's echogenic is because of reflection of sound. A lot of sound in comparison to other tissue interfaces is reflected. So let's say a typical tissue interface reflects only like 1% of the sound beam. Let's say, like, you know, muscle, skin, fat, muscle, each of those interfaces are actually reflecting very little of the sound beam. And then it gets down to the wall of the carotid artery. That's kind of, as far as sound is concerned, it's kind of reflective. It's like a mirror. And so a lot of sound is produced or is reflected back. Instead of 1%, let's just make it up and say 5%, which in ultrasound is actually a lot. That 5% reflection is actually really bright on the screen. And we'll talk about that, you know, the relative amounts of reflection. Oh, that's right. So we have different types of reflectors as well. There is the specular reflector or mirror. I forgot exactly. It's like, I think it's Greek. Specular is mirror in Greek. So what I've drawn here with this is a pulse, a single pulse of sound. It's traveling in this direction towards this interface. Well, we'll call this interface, meaning wall of the carotid artery is a nice example of an interface. There's thousands of them. I mean, there's all that fascia that we see in our neck, all those bright interfaces. Those are all examples of reflectors here. But a specular reflector is really special. It has properties in the tissue itself that just really makes it very smooth to ultrasound. So kind of like a mirror is smooth. So we know that in a mirror, if we shine a beam of, let's say like a laser beam at an angle to that mirror, it's going to come off on an angle. It's actually going to come off on the same exact angle, by the way. So, you know, this theta, that angle there is always going to be equal to that angle. So that's incidental and reflective. But we'll talk about that again in the future, very, very soon. So with a specular, and of course down here I've drawn a 90-degree angle, sound coming straight at it and then bouncing straight back. That's how you use a mirror, right? You stand in front of the mirror and you're able to look at yourself. If you stand off to the side of the mirror, you see the rest of the room, but you don't see yourself. So that's kind of obvious, but sometimes when it comes to explaining it in ultrasound, takes a little more. Specular reflectors, they reflect, I don't want to say 100%, but I'll just say large portion of beam. They really reflect a lot of the beam. So this is getting a little ahead of ourselves, but you can imagine if you have a beam coming down at this angle, and then it's going to reflect off at the same angle. Hopefully, I don't know how well you guys can see this, but I should have used a brighter color. If it's coming in at this angle, it's reflecting at that angle. It's not reflecting back to the transducer. So sometimes specular reflectors, they could be really bright in the case of 90 degrees, and they can sometimes disappear if you hit them at a really sharp angle, which is kind of interesting. But I'm getting ahead of myself again. Diffuse reflector, I have not drawn that in yet. Specular reflectors, by the way, are relatively rare in the body. Diffuse reflectors are everywhere. It's basically everything else is a diffuse reflector. So as a beam of sound comes in, let's use some brighter colors so you can see that a little better. Beam of sound comes in. Here's my little pulse. It's going in this way. As it hits this, it's gonna have some sound going straight back, but some of it's gonna bounce off in this direction. Some of it's gonna bounce off in that direction. Basically, the specular reflector was a mirror. The diffuse reflector is a wall. When we look at a wall, I'm looking at my wall right now, I can see all the texture and everything. There is light coming in from outside. It's hitting the wall and it's scattering in all directions. And some of it, only a small percentage of that light is actually getting back to my eye. If it were a mirror, a large, and I was at just the right angle, I'd be blinded because the sun would be in my eyes. But since it's a wall, it's not a problem, or it's not too bright. It's reflected all over the place. So that's a diffuse reflector. The surface yeah, that's a C. Scatters sound. Now, I usually draw this, the size of the arrow is indicative of the strength of the arrow. Yeah, perhaps if I'm hitting it at a 90-degree angle, yeah, probably the majority of it comes back, but still, a fair amount of energy goes off another direction, and that energy might very well be lost. So that's part of attenuation as well. Because obviously sound is going to continue on, but it's going to be weaker because so much of it was lost. So much of it was lost or reflected at that interface. As the sound travels on, it's going to continue to be weaker. Now scattering, and this is more of an interface between, let's say, the fat surrounding the kidney to the kidney itself. You're going through this beam of sound goes through the fat, then it hits the kidney, and the kidney's relatively a diffuse reflector, the wall of the kidney, that is. Now, diffuse, like I said before, specular reflectors are fairly uncommon, or they're certainly not the majority. Diffuse reflectors, when we're talking about interfaces between one tissue and the next, are more common. And then there's everything else. Everything else, every single cell and lobule and connection and everything else in the body is a scatterer. Well, except for red blood cells, but I'll tell you that in a second. Scatter. So like the middle of your liver, that's obviously not an interface. It's not the edge of the liver, between fat and liver. This is in the middle of the liver, is just liver cells and other things. There's arteries and veins and ducts. And all of those things cause just pure scattering. This is why ultrasound looks a little bit like sand, and grainy, right? It's very grainy, and it's because of scattering. So if you would imagine sound beam coming in, when it hits this, it's going to be coming, some of it, once again, some of it will go back straight towards the transducer, which is great. That's the part we see. And then others go off in this direction. So just like the wall, diffuse reflector wall, even some scatter off in this direction and then bounce again. So it really can become a complex mess of echoes. All right, there's another term. I skipped a term. I want to go back to it in just a second. That's why I got to keep this book open. Scattering. Many directions, tissue interface is small, equal or less than the wavelength. Okay, yeah. So, in the case of scattering, the size of the wavelength, the wave, oops, I did two wavelengths. No, I didn't. Whatever. Lambda wavelength. The size of the wavelength in the case of scattering is near, make sure I say this right, or less than the scatterer itself. So maybe I'll make my wavelength even smaller. So when the wavelength of the beam is about equal or smaller than the about equal or greater the wavelength. I'm sorry. I went from the wall to the scatterer, and it's the exact opposite, and I just set it backwards. Sound scatters when the tissue interface is small, that is equal to or less than the wavelength. Okay. Let me start over. I'm going to erase a bunch of these. Okay. I said it backwards. I was saying wavelength to tissue, and I should have been saying tissue to wavelength. In any case, when the tissue, let's see, the size of the tissue interface, as in like, well, a group of cells is sometimes called a lobule. or gosh, why can't I was to say like in the liver, there's hepatocytes and duct. Duct is a regular duct, but when it's ductule, that means it's extremely small. Size of the tissue interface, lobules, hepatocytes, ductules, arterioles, all the smaller things. When that is smaller, about equal or smaller than lambda, the wavelength, then we get scattering. Back here, in both the specular and the diffuse reflector, the interface is larger than the wavelength. And that kind of makes sense. Think of it this way. We already said, let's just get this a little smaller so I can fit more. We said this one is a mirror. We said this one was a wall. Between mirror and wall, you look in a mirror to see yourself. That mirror is large enough, the interface between the air and the glass is large enough for you to look at. It's basically larger than the wavelength. This is just an analogy. Well, you look at a disco ball, yeah, that might be reflective, but each reflective surface is really small and they're aimed at slightly different directions. You can't look at a disco ball and figure out how your hair is looking unless you get really close to it. And so it's kind of like that. The individual facets of the disco ball are smaller than the wavelength. I mean, not really wavelength of light, obviously, but that's the analogy, is that it's a smaller, that scatters, the disco ball scatters light in all directions. Your tissue is more like a disco ball. It scatters light in all directions. Actually, that analogy worked. I saved myself. I don't know about you guys. You guys are freaking out. But. So, oh, that's right. I said I missed a term, and this term is kind of important. So let me go back. I did say that the surface of a diffuse reflector scatters sound. The other term for that, for a diffuse reflector, is also backscatter. The only reason it's important to know the term backscatter is really referring to this diffuse reflector, because scattering itself refers to the disco ball, or the tissue itself, the microscopic tissue. Okay, I didn't leave myself a lot of room here. Let me just lasso this here. Okay, that should be good. Let's see, scattering also in many directions. High frequency sound beams scatter much more than low frequency beams. Scattering is related to frequency. I could still talk about that. And then there's Rayleigh scattering. Okay. Now I'm going to talk about frequency and scattering at the same time with both scattering and Rayleigh scattering. So this is the last one of the scattering we'll talk about is Rayleigh scattering. This is a special type of scattering. And this is actually why blood is usually, sometimes we do see blood, actual red blood cells moving on the screen. When you see that, it's probably because there's hundreds of them or at least dozens of them clumped together. And that's okay. They can clump together a little bit and travel in a group. It's not an embolism when that happens. They're just simply sticking to each other. But when they're spread out, you cannot see blood, even though we can see everything else. And so why is that? And blood's filled with all these proteins and it's filled with red blood cells, but yet it's usually anechoic on the screen, black on the screen. Well, when a sound beam, I'll come up from this direction. Oh, but this time I'm going to draw. When a sound beam hits a red blood cell, it doesn't scatter. Here, I'll show. First, I'm going to draw what it doesn't do. It's not like some of it goes this way, some of it goes this way, some of it goes this way, maybe a little piece goes that way. That's not exactly. That's more just regular scattering. With Rayleigh scattering, sound hits the red blood cell and it comes out a little bit right there, 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 there. In other words, all of the energy is dissipated in all directions. Well, see, that's not good for us and with ultrasound. Let me go back to scattering here. We might have had scattering here, but most, or let's I don't know about most, a good portion of this energy is actually directed back towards the transducer. Even though, yes, some of it's scattered in this direction and that direction, that energy is lost. But a good amount is still directed back towards the transducer. If it were not, we wouldn't see anything. And in the case of red blood cells, we usually do not see them. And that's because no more energy is sent back than is sent off to this side, that is sent off this way, that is sent in the opposite direction. It is basically so very only a small percentage of sound is reflected back to the transducer. Only a small percentage of sound. So Rayleigh scattering is not really our friend. Now with both types, frequency or an increase in frequency will increase the scattering. When it comes to Rayleigh scattering, it is a specific relationship there. And so that is, oops, Rayleigh, yeah. Oh, I got my E and my I mixed up, didn't I? That's okay. Rayleigh scatter is proportional frequency to the fourth power. So that's actually a big, anytime you see something to the 4th power, that's kind of a big deal. Let me read this and make sure I say it correctly. It's much smaller than beams. So starting over, special form of scattering that occurs when the structure's dimensions, the red blood cells in this case, dimensions, are much smaller than the wavelength of the beam itself. Rayleigh scattering redirects the sound wave equally in all directions. In clinical imaging, the interaction of ultrasound and red blood cells, Rayleigh. Rayleigh scattering increases dramatically with increasing frequency. When frequency doubles, Rayleigh scattering is now 16 times as high. Well, that's because 2 to the 4th is, that's a 2. I know it looks like my letter A's. 2 to the 4th is 16. So you increase your frequency, it really increases Rayleigh scattering. High frequency over here as well. So in regular scattering, let's see, where do I have room? Under the disco ball. I don't know what the exact relationship is. The book doesn't tell me and I've never looked it up, but an increase, phone scared the daylights out of me. You know, that was just uncool. You call me right back. An increase in frequency is going to cause an increase of scattering, but not at this level, not at the frequency of the 4th degree. Questions? Anyone freaking out yet? If you're not freaking out, I don't know what to say, because this is a lot. This is a lot to look at, but you know, if you read your book carefully, you might understand it a little bit better. Everything you really need to know is in the book. Remember, this guy writes half the test. Summary, reflection, scattering. Recall that higher frequency sound waves produce shorter pulses, which would create more accurate images. So high frequency, beautiful imaging. However, high frequency sound attenuates more. High frequency, can't see my liver. So that's our balancing act there. However, higher frequency sound attenuates more and is less capable of traveling. Thus, there's a conflict between image accuracy and attenuation. The goal is to use the highest frequency, still providing the clinical images, clinically worthy images. Well, like I said before, we would love to always use high frequency. We just cannot because of attenuation. So we've talked about, I just want to make sure, attenuation, reflection, scattering. So reflection and scattering they're not quite the same thing. Absorption, that's completely different. Absorption or heat. I already mentioned heat though, didn't I? When I talked about the interaction of the sound wave with tissue, each physical interaction, literally physically moving back and forth, steals from our beam, steals energy from the beam, and that is basically in the form of heat. So let's go back down to my beautiful thermometer here. That's just it, it's just a thermometer. The third most sizable, that's right, that's the important part to remember with heat. Absorption then is the number 3, but it is the number 1 cause of attenuation. Number 1 cause of attenuation is simply losing energy to heat. Remember, energy is neither created or destroyed, but it is misplaced. In this case, we're just misplacing it as heat. He also mentioned sound traveling in bone undergoes extensive absorption. That actually, so yeah, we can't really scan through bone. You know, every time we see a bone, we just see shadow. We see a bright echo where everything is, a lot is reflected at the surface, and then there's shadowing because the attenuation was so strong, we have a total lack of information. But it's important to know that bone undergoes extensive absorption when we're talking about fetuses. When they start to develop bone, at first it's not bone, of course. At first, fetuses have cartilaginous bones. Their bones are made of cartilage. That doesn't absorb a whole lot of heat, but then they start to calcify, and it really starts to absorb sound. And at that point, we have to worry about, at least the bioengineers and everyone who builds these machines, they really have to worry about how much heat we're developing. You don't want to cook the skull on a little fetus. Oh my gosh, attenuation coefficient. Let's see, what time is it? 11:11. Well, we're going to get into page number 2. I've got a whole nother one developed here, but we're not finishing it. Oh my God. So reflection, scattering, absorption. Those are the 3 big ones. Those are the 3 contributing factors to attenuation. Absorption being the most significant portion of that. We do have to calculate it. But calculating this it gives us a really good idea about at what rate of speed we're losing sound. And like I've told you guys before, you wouldn't believe it. We lose sound at a very high rate of speed because it's ultrasound. If we were using infrasound, you wouldn't attenuate at all. It'd just go right through your body. But then again, you wouldn't be able to create a picture at all with ultrasound. I'm sorry, infrasound. You wouldn't be able to create a picture. Okay, attenuation is a process whereby sound energy is extracted from a wave. Total attenuation depends on so we have an attenuation coefficient. Attenuation coefficient is the number of decibels of attenuation that occurs when sound travels 1 centimeter. Yeah. So we do have to talk a little bit about these decibels, don't we? The units of attenuation are decibels per centimeter. So attenuation, yeah, I always use a small letter A, subset C, attenuation coefficient, and that is in decibels per centimeter. So every centimeter we go, we lose X amount of decibels. It so happens that it works out pretty well that the attenuation coefficient happens to be frequency. I'm going to put frequency O for the operating frequency of 5 megahertz, 8 megahertz, 10 megahertz. Operating frequency divided by 2. And then that's it. That's the entire attenuation coefficient. So if I say, what's the attenuation coefficient of 5 megahertz, you would know because you could do math in your head so quickly, just like I can because I'm not looking to the side. It is 2.5 decibels. So if I were to say 5 megahertz is our operating frequency, just simply divide that by 2. And we get 2.5. Oops. Actually, I could have done that in my head. And it's decibels per centimeter. Okay. So attenuation is this one. See, there's no AC, it's just simply attenuation, and it's in decibels. It's not per centimeter here. It's attenuation overall. So that one, we're going to, let's say it's attenuation for this example, 5 megahertz. We know is, let's do this. Attenuation coefficient times, what was it? I guess it's just distance. I'm going to put D. D for distance, depth. That's in centimeters. Equals whatever it's going to equal. So let's use this example. Attenuation coefficient, we already discovered, is 2.5. Per centimeter. My example that I have written in my book is 3. So at 3 centimeters, I guess it'd help if I put attenuation decibels equals 2.5 times 3, which is going to be equal to 7.5 decibels of attenuation. In other words, and remember, the negative is, is implied. I think that's how you spell it. Anyway, negative is implied, or negative is assumed. Because attenuation is always negative. So you don't have to put negative there. You can, it's redundant, but just remember that it's always assumed negative because that's the only thing it does. Okay, well actually, so think about this. In 3 centimeters, we have 7.5 decibels of attenuation. Actually, we don't even have to look at that. Let's look back at our original. .5 decibels per centimeter. Well, what did we say? We said 3 decibels is an attenuation, so it's negative. 3 decibels is half. So every centimeter at a 5 megahertz, every single centimeter, we're almost losing half of the beam. So that means the first centimeter, half the intensity is gone. The second centimeter, half of that half is gone. The third centimeter, half of that is gone. Every single centimeter you're losing, well, I shouldn't say half, almost half is gone. That's really amazing. Every single centimeter, and that's at 5 megahertz. That's 5's low. That's a low frequency. Okay. So once again, you cannot find attenuation without either being given or first finding the attenuation coefficient. So if a question's starting here with what's the attenuation, well then the first thing you need to do is figure out what the attenuation coefficient is. Maybe they give it to you, maybe they don't. They might say, what is the attenuation of a 5 megahertz transducer at 3 centimeters. Okay, 5 megahertz transducer, now I have to go back, find the attenuation coefficient by using this very easy formula. Frequency divided by 2, find that. Oh, and of course, when we work it out down, we work it down to here. I forgot to cancel my centimeters, which is why we end up with decibels only. Okay. Let me read. Attenuation coefficient, units. For example, in sound 5 centimeters attenuation. Oh, the sound travels to a depth of 5 centimeters. Attenuation coefficient means 2 decibels per centimeter, and the total attenuation is 10 decibels. All right, I just basically did the same thing, except I went with 3 centimeters. The attenuation, one thing it's stressing here is attenuation coefficient does not change, whether it's 1 centimeter, 10 centimeters, 15 centimeters. That is once you find it, it's a constant throughout the body. Attenuation coefficient in soft tissue. Attenuation coefficient and frequency are directly related. Frequency goes up, attenuation goes up. The equation to the right apply the sound waves. Let me tell you something about, we have the half value layer thickness. Let me just read page 86. Thus far, we've learned the typical. Okay, yeah, well, compared to soft tissue, air, that's actually a good point. Air, believe it or not, has extremely high attenuation for ultrasound. And that kind of makes a difference too. Air has extremely high attenuation rates. Sound with frequency above 1 megahertz attenuates entirely. Entirely when? Well, basically, our megahertz, that sound doesn't travel through air at all. If it gets, that's even if it gets into, that's actually, towards the end of the chapter, we talk about reflection versus
AA meetings?
Transmission. Oh, God, I couldn't think of the word. When you go from tissue to air, it doesn't even go in at all. It actually entirely reflects. But even the little bit of sound that does get into the air attenuates very quickly because we're using frequencies that just simply can't travel through air. Let's see. Sound with frequencies above 1 megahertz attenuates entirely. Lung attenuates dramatically, not entirely, but dramatically. We don't see normal lung very well at all. Or really, we really don't see normal lung. Bone absorbs ultrasound energy to a large extent, so that attenuates. So air attenuates, bone attenuates. That's kind of interesting because it's not only attenuating, the sound that actually does get into the bone or does get into air attenuates quickly, but most of it doesn't even get there in the first place. And that we talk about in just like 3 pages here. Biological fluids is much less attenuation. We have patients fill their urinary bladder before doing a pelvic ultrasound. Urine barely attenuates the sound at all. The sound is just like a free ride all the way through the bladder. So that's a big reason why we torture our patients and make them drink water until they think they're gonna pop. Finally, water. Let's see, yeah, attenuation in muscle is interest. Attenuation properties of muscle are very strange, simply because sound attenuates twice as much when traveling across the fibers than along the length of the fibers. So if you have, you're doing the carotid ultrasound, you see the sternocleidomastoid muscle right here, and you see fibers running kind of more or less lengthwise. The sound attenuates faster, right? Yes, of course, twice as fast here than if you were able to see that muscle dead on, looking straight down the muscle, then the attenuation would be less, probably because you're not going through all those different interfaces. 1125. Okay, we're barely going to start on the second page. I do want to talk about half value layer thickness on this page. Did I have a, yes, little sectional, oh, I really prepared for this, didn't I? I wrote it down. And I didn't even finish with the NESS. All right, half value layer thickness. Well, this is kind of it's really, I don't know why we even bother. Because we've already, this is basically the same thing. It's the same thing as attenuation. It's the same thing as what we just found out. Another term that helps simplify the discussion of attenuation is half value layer thickness. It's kind of like if anyone knows what a half-life is of a radioactive material. A half-life might be a week, a year, 10,000 years. It's how long it takes for half of a radioactive a radioactive substance to radiate away, or to at least undergo radiation. Half value layer thickness is how much tissue you need to go through before you lose half of the value. Well, I don't understand that. You know, we kind of figured that out over here, didn't we? 2.5. We're really close to it. In fact, if my answer turned out to be 3, it didn't, it was 3.5, but if it turned out to be 3 decibels per centimeter, then that would be whatever length it took to get to 3 decibels is my half value layer. So there's one thing I believe it or not, I actually figured out without having to read a book, was half value layer thickness happens to equal three decibels divided by the attenuation coefficient. So half value layer thickness is a distance sound travels in tissue that reduces the intensity of sound to 1/2 its original value. In other words, 3 decibels. The half value layer can also be the depth of tissue that results in 3 decibels of attenuation. The units of half value layer are centimeters or any other unit. Typical values to lose half of your energy, 1/4 to 1 centimeter. Crazy. Half value layer is known by other names. It's penetrating depth, depth of penetration, half boundary layer. We'll just remember half value layer thickness is the distance it takes to go to lose half of the sound, which is really the same thing as attenuation. It's just looking at it from a different way. High frequency, of course, is going to be a thin or a not very deep layer. Low frequency is going to produce a half value layer that is, of course, much deeper. Let's see. I do have a little example written down here, so let's use that. Let's see. Half value layer of 2 megahertz. Is it 2 megahertz? Did I want to use 2 megahertz? Didn't, that was 5 megahertz. Okay. So if I just look at, if I just want to use this guy, 3 decibels divided by the attenuation coefficient, we're going to have to find the attenuation coefficient. Frequency divided by 2 is the attenuation coefficient. So for some odd reason, I decided to use 2. So attenuation coefficient is equal to 2 megahertz. So in other words, what is the half value layer using a 2 megahertz transducer? 2 megahertz transducer divided by 2. Well, 2 divided by 2 is going to be 1. So 1 decibel per centimeter. It kind of makes sense. 2 megahertz is as low as we ever go. So 1 decibel per centimeter is the best we could ever expect from attenuation. In other words, you want as little attenuation as possible. So the half value layer, I can see why I use 2 because that makes 1. That makes this easy math. 3 decibels divided by the 1 decibel per centimeter is going to equal 3 centimeters. Cross out our decibels. So even with the lowest frequency available to us, and actually I don't think our transducers go down to 2 megahertz, so not really available to us, available to other sonographers. But even the lowest frequency, you still lose half of your energy by the time you've gone 3 centimeters into the body. Okay. I'm not prepared to do a review. I actually would prefer to pull up the test. I'll tell you what, guys. I am going to create another video. You won't be able to ask me questions, but you can ask me questions. You can text me, email me. Of course, anytime. But I'm going to create, I'll create a quick review video. Yeah, and I'll post that. I'll post that today. It'll just be called 4 or 5 review. Because I want to get just a little bit into the next page. Open recent. No. I'm so proud of this page. So proud of that. I wanted to start you with the concept here. We're not going to finish it, but I just wanted to start something. The next few pages in our book, we talk about reflection. Look at that, pretty fancy, huh? Reflection, transmission, and refraction. All of which is happening all the time when we're using our transducer. So diagnostic ultrasound is all about reflection, the echoes, and scattering. Actually, scattering is more important than reflection, but they're all bringing the echoes back to us. But without transmission of the beam, we have nothing. In other words, if I have a beam coming down here, and hits an interface and 100% of it goes back, well, I see a really bright line and that's it. No information. No information can be seen back here because 100% of my sound is reflected. You guys, we see that every single day when the transducer is on, but it's just simply sitting with no gel on it. It's just sitting, waiting to be used. You look at your screen, you see a very, very bright echogenic line at the very top of your screen. That's 100% reflection. That's what 100% reflection would look like. And of course, we see nothing of use at all beyond that bright line. And we actually see bright line, bright line, bright line. That's reverberation, but it's all just considered the same line. It's simply not useful to have 100% reflection. So you have to have transmission. In fact, you have to have a lot of transmission, a lot more than you would think. Every single interface has to have a lot of transmission. Otherwise, the attenuation would be too much. So to determine if a tissue interface reflects sound, or what percentage of sound reflects, we need to know its impedance. Impedance, capital Z is the symbol for impedance. Impedance is acoustic resistance. It's how much sound is impeded by tissue. Now, I just want to get through a couple of concepts so you can ruminate on that until Monday. Wait a minute, what day is it? Yeah.
Friday. It's
Yeah.
Friday.
I was like, wait a minute, today Thursday? Please tell me it's not. How much sound is impeded by tissue? And just really quickly, Z impedance is measured in a term called Rales. It is found by finding the density, I believe this is rho is dense. I think that's the term for the Greek letter. That's a funny looking P on purpose. That means density times the speed of sound. So I have a little guy here on the beach, and there's a blue whale out in the ocean. In fact, he's pretty close to the beach. And blue whales, you may or may not know, are the loudest. Yeah, they are not only the biggest animal in Earth's history, but they are probably one of the loudest animals in Earth's history as well. They can produce sounds so loud that some researchers believe that halfway around the world, blue whales can hear each other. At least before we filled the seas with boats.
I thought you said Mariah
Oh! Well, I didn't hear that you, that was like a super scratchy.
Carey. It was Mariah Carey.
At least
You're
it's
banned
happened to
from
John and not you this time.
You're banned from talking. You could send me one of your smart aleck texts. So anyways, supposedly they can actually hear each other around the world, at least pre-industrial. But they could be 100 yards off the shore, you won't hear a thing. Right? Have you ever gone to the beach and like hear all the whales and the dolphins? You don't hear that. Not unless you're in the water, not unless, especially if you have a microphone in the water. The reason being is that they produce this incredibly powerful sound beam. Yeah, well, Mariah Carey's not the loudest, just the makes my ears bleed. Anyway, so we have this sound coming out of this blue whale, extremely loud. What happens at the surface of the water? It reflects. Never gets into the air at all. You cannot hear a whale from the beach, even though they are incredibly loud. And the same thing, you could be Mariah Carey. Here, let's put a little hair on her. And she can be, super high frequency. So, Mariah Carey's high frequency sound is going to be reflected off the water as well, and the blue whale is spared. And you guys have all seen that, you're in a pool, you could be yelling at someone down there. Of course, they're not going to hear you, and if they're down there, you might hear the slightest sound, but that sound is probably being transmitted through the sides of the pool rather than the air itself. So that's what our impedance, when we're going to look at impedance more on Monday. Our impedance tells us, does sound transmit, or how much sound transmits. The other overall concept then actually, you know what? I don't quite get into the other concept just yet. So just down at the bottom, I put an important reminder. Let me say it again. Impedance tells us if and how much reflection there will be at a boundary. So in other words, the opposite of saying does sound transmit is does sound reflect. And how much. Yeah, let's end it there, because we only have control save. Are you not? I guess it's already saved. Okay. Yeah, I don't want to. That's already a hard enough concept to deal with. We'll start again on Monday with. Well, we could review the first part of chapter 6 on Monday, and then quickly, and then get back into this page and go through it. So I'm sorry, I didn't pull. I can stop.